example using Gauss's law. We want to find an expression for the electric field caused by an infinite line charge. So this is taking point charges and just sort of stacking them all up one upon the other in a line. And we're taking it to be an infinite line charge because that actually makes it a little bit easier. We can do this basically algebraically instead of using intervals. All right, so our line charge is going to have a strength lambda, which is going to be the total charge of the line charge divided by the total length of the line charge. Those two are both going to go to infinity. The total charge goes infinite, total length goes infinite, but their ratio is finite. Now, applying Gauss's law, we need to pick a surface that we're going to apply Gauss's law to. And I want to pick a surface that shares the same sort of symmetry as this line charge. I want to have a surface where I'll have points that are all an equal distance away from the line charge. And so I'm going to pick this to be a cylinder. And the axis of the cylinder is coincident with the line charge. So there's the other cap on the back side. And this cylinder is going to have some radius r, and it's going to extend for a length L. And thinking about what the electric field is going to do, an electric field line is not going to be able to tilt left or right. Since this is an infinite line charge, I will always have just as much charge causing the field to the left as I will to the right for any point along it. So the only direction an electric field line can point is radially away from the line charge. So this cylindrical Gaussian surface is helping me capture that same symmetry. So this green cylinder is the Gaussian surface I'm going to use. And applying Gauss's law. So Gauss's law is going to tell us that I add up all of the flux of the electric field through my cylinder, and that has to equal how much charge is enclosed by the cylinder divided by the permittivity of free space. Now my Gaussian surface, I'm going to have 1, 2 end caps that are circles. So I'll label that 1. This surface, the end cap is 3, and then the side of the cylinder I'm going to call surface 2. So we go to evaluate the left-hand side in Gauss's law. We want to look at the flux of the electric field. The flux of the electric field is going to be the sum. I'm going to have the flux of the electric field through the left end cap. I'm going to have the flux of the electric field through the side of the cylinder, and then the flux of the electric field through the right end cap. So there are 3 surfaces. Now, since the electric field is going to have to point radially away from the line charge, and it can't tilt left, it can't tilt right, no electric field line can penetrate the end cap 1 or the end cap surface 3. So there can't be any flux through those. So I can set those to 0. and all of the flux is going to come through the wall of the cylinder. So just sort of collecting where we're at, the flux of the electric field is just the electric field flux through this wall of the cylinder. All points on that wall of the cylinder are an equal distance away from the line charge. If you think of like the perpendicular distance away, and so any point on this cylindrical surface, surface 2, is going to have the same value for the magnitude of the electric field. So in computing the flux, I'll have a constant magnitude, and then I just need to know the area of the wall of the cylinder. Well, what that's going to be, I just like taking a sheet of paper and wrapping around on itself to make a cylinder. I'm going to have a sheet of paper that is 2 pi r long in one direction, and it's L long in the other direction. So this area is going to be 2 pi r times L. So we have computed the left-hand side from Gauss's law. Now we need to think about what goes in the right-hand side. So we need to know how much charge is inside our cylinder. Well, that total charge is going to be our strength of our line charge, lambda, times L. So now we know both sides of Gauss's law, and we can set up our final equation where we're going to solve for the magnitude of the electric field. So the magnitude of the electric field times 2 pi r little l is going to equal the line strength, lambda, little l over the permittivity of free space, epsilon naught. And the length of my Gaussian cylinder is arbitrary. It's on both sides of the equation, so I can throw it out. And we can solve for the electric field magnitude. I'm going to have a lambda in the numerator, a 2 pi epsilon naught, and then the radial distance away from the cylinder, or away from the line charge, r. Now, since lambda has units of charge per unit length, I still need 1 power of length in the denominator, and that's coming from this distance away from the line charge, the radial distance, my r. So for a line charge, the electric field magnitude falls off as 1 over the distance. For a point charge, it's 1 over the distance squared. So the effect of having all of those point charges together in a line is going to make an electric field that's less strongly dependent on distance than a 1 over distance squared law.